Welcome back to another example in the stiffness method. In this lecture, we will solve another truss, an indeterminate truss using the stiffness method. However, since we've already covered the theory, this lecture now will very much focus on the coding, so going over the truss and then full implementation in MATLAB. Let's get on to it. In this slide, we're recapping the overall workflow for calculating reactions and internal forces using the stiffness method. We've already covered all the theory behind each of these steps in previous lectures, including how to derive the stiffness matrices, assemble the global system, apply boundary conditions, and compute reactions and internal forces. Those lectures also demonstrated how to carry out each part by hand, and they're all clearly titled according to the relevant topics, so you can revisit any of them if you'd like to revise the background or see some more worked examples. This lecture, however, will focus purely on the coding implementation, taking the theoretical steps and translating them into a structured MATLAB workflow. So on this slide, we're just outlining the full workflow that we'll follow when coding the stiffness method. We've already done all of these steps in the theory we developed, so we're not going to revisit theory, just show how we implement it. You'll also notice that I've made a few small tweaks to the order of operations compared with how we originally developed the method step by step. When we were building the theory, inputs naturally appeared at the moment they were needed. In actual coding practice, however, that leads to inputs being scattered throughout the script. So in this final version, all the input information is grouped right at the beginning. So the node coordinates, the connectivity, the material, the section properties, the loading, etc. It makes it much easier to see where everything goes, and also easier to adapt the code for other structures. So just to be clear, this reordering doesn't change the method at all. It's just cosmetic and just makes the script more user-friendly. The workflow then continues with computing element geometry, forming local stiffness matrices, rotating each element into global coordinates, and assembling the full global stiffness matrix. We then define the global load vector, apply the boundary conditions, and solve for the nodal displacements, and then recover the support reactions, compute the internal element forces, and report the full set of results. And this is the truss example that we will be solving step by step using the stiffness method. It's a planar truss with loads applied at the nodes. All members have the same material and section properties, and a Young's modulus of 200 gigapascals, and a square cross-section of 40 by 40 millimeters. What is particularly important about this example is that the truss is statically indeterminate. That means that we can't determine the internal member forces or support reactions using equilibrium equations alone. Instead, we must account for compatibility of displacements and the stiffness of each member. This is exactly where the stiffness method becomes essential. So rather than solving this using traditional truss methods, such as the method of joints or sections, we will formulate and solve the global stiffness system. This will allow us to determine the nodal displacements first, and then recover reactions and member axial forces. Before we start defining any structural data, the first step in our coding workflow is simply preparing the MATLAB file. This is mostly housekeeping, but it's an important habit to establish because it ensures that every run of the script starts from a clean, predictable state. So at this stage, we clear the workspace, close any open figures, and clear the command window. This prevents old variables or previous plots from interfering with a new analysis. We'll also add a header to the script to label the example and units used, which is very useful when you build up a library of analysis files. We now define the geometry of the truss through two key inputs: the nodal coordinates and the element connectivity. First, the nodal coordinates specify the position of each node in the global coordinate system. Each node is assigned an x and y location. In this example, it is convenient to start the coordinate system at one of the bottom end nodes of the truss. So we'll take the left support as node 1 with coordinates 0, 0, and this simplifies the geometry as all other node positions are then defined relative to this point. So node 2 is at 2, 0, node 3 at 4, 0, and so on. Second, the connectivity matrix defines how the nodes are linked together to form elements. Each row represents a member and identifies its start and end node. For instance, the first entry, 1, that's member 1, and it's between nodes 1 and 2. Diagonal member 7, for example, is defined between nodes 2 and 7. Together, these two inputs completely describe the structure. The coordinates define where the nodes are, and the connectivity defines how they're connected. For a truss, this is sufficient to determine each member's length and orientation, which we will use shortly when forming the stiffness matrices. It is essential that the node numbering and connectivity are consistent, as any errors here will propagate through the entire analysis. In this step, we assign the degrees of freedom to each node of the truss. For a 2D truss, each node has 2 degrees of freedom, the horizontal displacement u and the vertical displacement v. So we set number of degrees of freedom, num_dofs, to 2 to reflect that. Next, we count how many nodes and how many elements the structure has, based on the input that we entered in the previous set. The loop you see here automatically numbers the degrees of freedom for every node. So node 1 gets degrees of freedom 1 and 2, node 2 gets 3 and 4, node 3 gets 5 and 6, and so on. This continues all the way up to node 8, which will end at degrees of freedom 15 and 16. The table shown in the slide is exactly what MATLAB produces. Each row corresponds to a node, and the 2 columns list its assigned degrees of freedom. This numbering system is extremely important because it tells the code where each element's stiffness contribution belongs inside the global stiffness matrix. It is the link between the individual truss members and the behaviour of the full structural system. In the next step, we define the material and section properties for the truss element. These values directly feed into the stiffness matrices that we derived in the theoretical lectures. Here we're using 200 gigapascals, which is typical for structural steel. We'll multiply to convert from gigapascals to pascals because we're going to be working in SI units. The line E equals E0 times 1s simply assigns the same material property to every element. Next, we define the cross-sectional area A of each member. In this example, our truss had a 40 by 40 millimeter square section, so we convert that into square meters using the factor 10 to the power of -6. Again, the line A equals A0 times 1s assigns the same area to every element in the truss. In this example, we've assumed that all truss members have the same material and cross-section. However, this is not a limitation of the method. It is very straightforward to assign different properties to different members by defining E and A individually for each element. These inputs complete the physical description of the truss, and from here, the code can proceed to compute element geometry and stiffness. Now we can define the loads acting on the truss. Just as with the material and geometric inputs, bringing all the loads into one place at the beginning of the script makes the code much easier to modify later. In this example, we only have nodal loads, which is typical for truss analysis. These forces are applied directly at the nodes that they act upon. The format used here is node fx fy. So looking at the inputs, at node 3 we have a 12 kilonewton downward force, and since downward forces are negative in the global y direction, this appears as minus 12,000 newtons. At node 6 we have a 15 kilonewton downward force, which is entered as minus 15,000 newtons, and at node 8 we apply a 10 kilonewton horizontal force acting to the right, which appears as plus 10,000 newtons in the global x direction. Next, we define the boundary conditions. These specify which degrees of freedom are restrained. The code uses the degree of freedom numbering that we established earlier, so we refer directly to entries in the degree of freedom mapping matrix. For example, node 1 is a pin, so it is fixed in both the x and y directions. So both its horizontal and vertical degrees of freedom are restrained. The other supports are roller supports, so they only restrain one direction. Together, the loads and boundary conditions now fully define how the truss is acted upon and supported, completing the input required before assembling the global system. And now that all the input data has been defined, the first computational step is to determine the geometry of each truss element. This includes the element length, the direction of cosines cos theta and sine theta, which describe the orientation of each member relative to the global coordinate system. We begin by creating arrays to store the length, cosine, sine, and angle for every element. Then we loop through each element using the connectivity information defined earlier. Inside the loop, we extract the coordinates of the element's start node and end node. From these, we compute the horizontal and vertical projections dx and dy. The element's length is then calculated using Pythagoras, so L equals a square root of the sum of squares of dx and dy. Next, we can calculate the direction cosines, so cos theta is dx to L, and sine theta is dy to L. Those direction cosines are essential because they define how each truss member is oriented in space. They will be used to transform the element stiffness matrix from the local coordinate system, where the formulation is simple, to the global coordinate system used for assembly. We'll also store the angle using a tan 2 dy dx, which returns the orientation in radians. This is mainly useful for checking or reporting results and can be converted to degrees later if we need to. This entire step is carried out automatically once the nodal coordinates and connectivity are defined. So if we change the geometry of the truss, the code will update all element properties accordingly, ensuring the stiffness formulation remains consistent. Here we compute the local stiffness matrix for each truss element. This is the matrix that captures the axial behaviour of the member in its own local coordinate system, exactly as we derived in the theoretical lectures. For a truss element, the stiffness matrix is based on the axial stiffness term, EA, divided by the element length, L. Inside the loop, we retrieve all the relevant properties for each element, so Young's modulus E, the cross-sectional area A, and the length L, and we use them to compute the stiffness matrix. The resulting matrix is a 2 by 2 matrix with the form of EA over L times the matrix of 1 minus 1, and then in the next row minus 1, 1. This reflects the fact that the element resists deformation only along its axis, and that equal and opposite forces develop at the two ends. In the next step, we transform this matrix into the global coordinates so that all elements, regardless of their own orientation, can be assembled into a single global system. So, as we said, now that we have the local stiffness matrix for each element, the next step is to rotate it into the global coordinate system. This is essential because each truss element is defined in its own local axes, as we said, along the member, but the structure as a whole is assembled in the global xy coordinates. So to do this, we use the transformation matrix T, which is built from the direction cosines we calculated earlier. For a truss element, this matrix maps the global nodal displacements u1, v1, u2, v2 into the local axial displacements at each end of the element. The matrix T uses cos theta and sin theta to resolve global displacements into the local axis of the member. Once the matrix T is formed, the global stiffness matrix for the element is computed using T transpose times the local stiffness times T. This rotates the element stiffness from the local coordinate system into the global coordinate system, so that its contribution is aligned correctly with the global degrees of freedom that we identified earlier. Once all the elements are transformed, we're ready to assemble them into the global stiffness matrix. The global stiffness matrix represents the behavior of the entire structure and is built by combining the contributions of all the individual elements. We begin by initializing the global stiffness matrix K as a zero matrix of size equal to the total number of degrees of freedom. Then, for each element, we identify the global degrees of freedom associated with its start and end nodes using the degree of freedom mapping matrix N that we defined earlier. For a truss element, that gives us 4 degrees of freedom, U1, V1, U2, V2. The element stiffness matrix, which is now a 4 by 4 matrix in global coordinates, is then added into the corresponding locations of the global stiffness matrix. This is done using the degree of freedom indices to place each term of the element matrix into the correct position within K. If multiple elements are connected to the same node, their stiffness contributions accumulate at the same degrees of freedom. This is how compatibility between elements is enforced in the stiffness method. By looping through all the elements and assembling their contributions, we construct the full global stiffness matrix for the structure. This is the foundation of the system of equations that we will solve next to obtain the nodal displacements. We now construct the global load vector. This vector contains all the external forces applied to the structure expressed in terms of the global degrees of freedom. We begin by initializing the load vector F as a zero vector with a size equal to the total number of degrees of freedom in the system. In a truss example, loads are only applied at nodes and only in the global x and y directions. Before assembling the loads, we include a small safeguard in the code. If no nodal loads are defined, the variable is set to an empty array. This prevents errors and allows the code to run even if no loads are applied. We then loop through each row of the nodal load input. For each load, we extract the node number, the horizontal force Fx, and the vertical force Fy. Using the degree of freedom mapping matrix N, we place these values into the correct positions in the global load vector. The horizontal force is assigned to the degree of freedom U and the vertical force to the V degree of freedom. If multiple loads act at the same node, they are automatically summed through this process. The resulting vector F represents all external forces acting on the structure in a form that is compatible with the global stiffness equation. And this completes the loading definition, and we're now ready to solve the system of equations. So, we can now solve the stiffness equation to obtain the nodal displacements. We begin by identifying all degrees of freedom in the system and separating them into free degrees of freedom and restrained degrees of freedom, based on the boundary conditions defined earlier. The free degrees of freedom correspond to unknown displacements, while the restrained degrees of freedom are fixed and therefore have zero displacement. Next, we form the reduced system of equations. Instead of solving the full system, we extract the submatrix corresponding only to the free degrees of freedom. This gives us the reduced stiffness matrix KFF and the corresponding load vector FF. The reduced system takes the form KFF times DF equals FF. We then solve this system to obtain the unknown displacements at the 3 degrees of freedom. Once these are known, we can reconstruct the full displacement vector. We initialize the full vector zeros, and then we insert the solved displacements at the 3 degree of freedom locations. The restrained degree of freedoms remains 0, as required by the boundary conditions. The result is the complete displacement vector D for the structure, which is shown on the right. This vector represents the deformed shape of the truss and forms the basis for computing reactions and internal forces in the next steps. With the full displacement vector now known, we can compute the support reactions. These are the forces required at the restrained degrees of freedom to enforce the boundary conditions. Essentially, the forces the supports must provide to keep those degrees of freedom fixed. The calculation comes directly from the global equilibrium equation, R equals Kd minus F. This gives the reaction force at every degree of freedom in the structure. From this full reaction vector, we then extract only the entries corresponding to the restrained degrees of freedom because reactions only occur at the supports. These are the values shown in the table on the right of the slide. The diagram underneath highlights where those reactions occur in the truss. Since this is a truss, the supports provide only horizontal and vertical reactions, no moments. You'll notice that some reaction values are positive and some are negative. This simply reflects the global sign convention. A negative value means that the reaction acts in the opposite direction to the assumed positive direction, which is completely expected. Now that we have both displacements and reactions, the final step is to compute the internal axial forces in each truss member. So, for a truss, we only have axial forces, since members do not carry shear or bending. We'll begin by preparing containers to store the results. NLM stores a single axial force per element, and F local all or F lock all stores the local end forces for each member. For each element, we carry out the following steps. Extract the element degrees of freedom, identify the global degrees of freedom associated with the start and end nodes using the degree of freedom mapping matrix N. This gives us the element degree of freedom vector corresponding to U1, V1, U2, V2. We extract the element nodal displacements, and using the global displacement vector D, we assemble the element displacement vector DE. We transform the displacements into local coordinates, and we use the transformation matrix T to rotate those global displacements into the local system, giving UL. This represents the axial displacements at the two ends of the element. We can then compute the internal forces. The local internal force vector is given by F local equals K local times UL, and the resulting 2x1 vector contains the axial forces at the two ends of the element. These are equal in magnitude and opposite in sign, ensuring equilibrium within the member. And finally, we report a single axial force per element taken from one end. By convention, tension is taken as positive, so a positive value indicates that the member is in tension, and a negative value indicates compression. These axial forces are the key results for truss analysis and form the basis for member design and assessment. With all the element forces computed, we can now move on to presenting and interpreting the results. And the final step of coding workflow is reporting the results. This is where everything we've computed, geometry, loads, displacements, reactions, and internal forces, is printed in a clear, readable format. The reporting section does several things. Displays the global stiffness matrix, mainly for verification. We don't expect to interpret the full matrix by eye, but it's useful when debugging or checking smaller examples. We have an output of basic element information, so we print element lengths, element angles. These confirm that the geometry has been correctly interpreted from the input data. We display the global load vector, and printing it allows us to verify that the loads have been applied at the correct nodes and in the correct directions. We print the nodal displacement vector. This is the key output of the stiffness method, the global displacement field of the structure. These values drive all the calculations of internal forces that follow. And we show the support reactions. Only the reactions of the restrained degrees of freedom are displayed. These should balance the applied loads, providing a direct check of global equilibrium. And of course, we print the internal element forces. For each element, the code reports a single axial force. And this completes the full stiffness method workflow for the truss example, from defining the inputs through to computing the displacements, reactions, and internal axial forces. To validate our results, we now compare the support reactions obtained from our code with those from an external solver. In this case, I've used the Behaviour truss calculator. On the left, you can see the same truss model set up in the calculator with identical geometry, supports and applied loads. And on the right, I've got the reaction forces reported by the calculator alongside the values computed by our MATLAB code. If you compare those results, you can see that they match very closely. Any small differences are due to rounding, as the calculator reports values to a limited number of significant figures. For example, the horizontal and vertical reactions at node 1, as well as the vertical reaction at node 4 and the horizontal reaction at node 5, are consistent between both approaches. This agreement is very important. It confirms that our stiffness formulation, degree of freedom mapping, boundary conditions, and solution procedure have all been implemented correctly. It also gives us confidence that the displacement field and internal forces computed earlier are reliable. Validation like this is a key step in any computational workflow. Before using a model for design or any further analysis, we should always check it against a trusted reference or simplified solution. We now compare the internal axial forces obtained from our code with those from the Behaviour truss calculator. On the left, you can see the same truss model used in the external solver, and on the right, we have the axial forces reported by the calculator alongside the values computed by our MATLAB implementation. Each element is listed with its corresponding axial force, and as before, tension is positive and compression is negative. If we compare the results element by element, we can see that they match up very closely. The magnitudes and signs are consistent across all members, with only very small differences due to rounding. For example, members carrying significant tension, such as elements 1 and 5, show strong positive values in both results, and members in compression, such as 4 and 11, have negative values that align closely between the two solutions. This comparison also provides a strong validation of our implementation. It confirms that not only the global response, but also the internal force distribution within the truss has been captured correctly. And finally, we can compare the nodal displacements obtained from our code with those from the Behaviour truss calculator. On the left, you can see the same truss model analysed in the external tool, and on the right, we have the displacement results from both the calculator and our MATLAB implementation. Each node has two displacement components, the horizontal displacement u and the vertical displacement v. If we compare the values node by node, we can see that the results match very closely. Magnitudes and directions are consistent, with only very small differences due to rounding. You'll also notice that some nodes have zero displacement. Those correspond to the restrained supports with the boundary conditions in force zero movement. The remaining nodes show small displacements, typically on the order of 10 to the minus 4 to 10 to the minus 6 meters. Although those values are small, they are essential as they govern the internal force distribution within the truss. This final comparison completes the validation of our implementation. We've now verified displacements, reactions, and internal forces against an independent solver, giving us strong confidence in the results. To summarize, in this example, we've taken an indeterminate truss, defined its geometry, material properties, loads, and boundary conditions, and solved it using the stiffness method. We computed nodal displacements, support reactions, and internal axial forces, and confirmed their accuracy through comparison. Most importantly, this code now gives us a powerful tool. As long as we understand how the stiffness method works, how the inputs are defined, and how to modify them correctly, we can use this same program to analyze much more complex and highly indeterminate truss structures in a systematic and efficient way. Thanks for joining me for the full coding of an indeterminate truss using the stiffness method in MATLAB. I hope you enjoyed it, and even if you didn't, you might want to take this example, slightly adapt it, or do a completely new example. That's when this method really starts to click. So enjoy!